and convert that to a secondary set of units. So, for example, if I know how many kilometers a particular distance is, I can convert that to miles using this equality. All I have to do is set up an appropriate conversion that allows my kilometers to be canceled out and my miles to be converted in the process. And so that's where these two kinds of fractions come in. And which fraction you use depends solely on what you're starting with and what you're trying to convert. Because every single conversion factor is going to follow this format. And the format is this. I have a unit that I'm starting with, and I'm trying to cancel out. So if that unit is in the numerator, we're going to find that that unit shows up in the denominator of our conversion factor. And those two would end up canceling out. I would get what I wanted. If the situation were to exist where the opposite was true, let's say that I had 1 over my initial units. Well, that would just mean that I would need to flip the fraction around. My initial units are going to go up here in the numerator. My desired units in the denominator. And the initial units would cancel that way. So regardless of what kind of a conversion I'm trying to do, that's ultimately going to be how I set it up, is to set it up in such a way that allows me to cancel out the things that I don't want and to leave behind the things that I do. Now, the case with any kind of calculation, especially unfamiliar calculations, is that practice is going to solve most of our problems. And so what we've set up in this are a number of practice problems to help us with that. Now, before we get to those, understand here that there are lots of different types of conversions. We highlighted on Friday these conversions here in terms of conversions of mass. Understand that there are other common conversions as well, most notably distance conversions, where we can convert inches into centimeters, centimeters into meters, meters into kilometers, and so on. We also have volumetric conversions. Volumetric conversions can focus in on cubic volumes like cubic feet, cubic meters. They can also focus in on more familiar kinds of volumes like liters and gallons, quarts. So volumetrically, there are usually quite a few options available to us. Understand that these conversions of cubic arrangement are set up as triples, basically, cubes of the interconversions between the distance measurements themselves. We can prove this to ourselves. If I want to convert 1 foot into meters, this is the conversion that I need to use. To turn it into a cubic foot and cubic meters, all I need to do is cube each of those quantities. So 1 cubed is 1. 0.3048 cubed is 0.02832. So that system, these numbers here do match up with the arithmetic algebraic manipulations of those conversions in the cases of cubes and squares and so on. So when we do dimensional analysis kinds of problems, there's a approach that we should look to take. First of all, we needed to figure out, what are we being asked to do? What conversions are we being asked to make? And once we know that, then we can start to look for ways to bridge the units together. So what relationships do we know that exist between the two unit sets that we're trying to convert? Do we have a conversion between them directly? If we do, that's great, we can use it. If we don't, can we find an indirect path to allow us to do the conversion and do it properly? Once we have that, we can set up the problem just logically speaking, using that unit canceling setup that I showed you on the previous slide. And then we have to ask ourselves some questions. Does our unit make sense? Do our units make sense? Have we canceled out everything that we were supposed to cancel out? And do the numbers make sense? So, for example, if I'm converting between millimeters and meters, I know that a millimeter is smaller than a meter. So if I have lots of millimeters, I should have very few meters. And if I'm going the opposite direction, if I have very few meters, I should have more millimeters because of that difference in scale. And so if I'm not seeing that, if I'm seeing that I'm getting the opposite effect, where the small unit gets smaller after the conversion, the big unit gets bigger after the conversion, then that's a sign that maybe I didn't set up my dimensional analysis correctly and I need to go back and reinvestigate. So let's go and do some of these problems. And so we're going to have 3 here that we're going to do. First one, how many inches are in 2 kilometers? Second, what is the volume of a 14 pound block gold if we are given its mass and its density? And can we convert a measurement of speed from miles per minute to feet per second? So let's look at them individually here. First one, how many inches are in 2 kilometers? The way about going to do this, again, we set up what do we know and what don't we know yet. So I have 2 kilometers. In the end, I'm going to try to convert that into inches. Now I know that there is no direct link between kilometers and inches. Luckily, as you can see in the space here, we've been given some information. Now, the information that we've been given is a combination of the information that we saw on Friday using the metric table and the information that we have in that reference table that I just showed you. Setup, well, I've got 2 kilometers. Since kilometers is in my numerator here, my first conversion factor should have kilometers in the denominator so that the kilometers cancel out. Because in the end, I don't want kilometers, I want inches. So every unit that I have that is not inches needs to cancel out by the end of the practice. I'm going to use this first conversion and go between kilometers and meters. Conversion says that there's 1,000 meters in every kilometer. My kilometers cancel out. My second conversion shows that there are 100 centimeters in every meter. Again, look how I set it up. I had meters in the numerator here. Meters will be in the denominator here so that the meters cancel. My last conversion, I need to convert centimeters into inches. I can see centimeters in my numerator here, so centimeters needs to be in the denominator here so it cancels. Inches will be in the numerator. The conversion is 1 inch for every 2.54 centimeters. And so I go to do all of my calculations. I see my kilometers have canceled, my meters have canceled, my centimeters have canceled, my inches have not canceled, but that's what I'm trying to find anyway. So that's what I want. To do the mathematics, I multiply by everything in the numerator and I divide by everything in the denominator. So I get 2 multiplied by 1,000 multiplied by 100 and divided by 2.54. All of the ones here, multiplying and dividing by 1 leaves the number exactly the same, so I don't need to do anything with it. I can just leave it as it is. My calculator spits out 78740.157 inches. How many significant figures do I need to round my final answer to? The answer here in this case is actually just 1. Should only have 1 significant figure at the end of this. Why only 1 significant figure? Well, it's actually pretty simple. Remember, when we multiply and divide, the number of significant figures is usually dictated by the significant figures in the things that we're multiplying and dividing. And we always round to the fewest significant figures out of that grouping. Well, this measurement, 2 kilometers, only has 1 significant figure. These other measurements of distance, these are actually exact calculations. And if we have exact calculations, defined values like these, they don't actually impact significant figures at all because they are said to have an infinite number of significant figures. If I have something that is exact, then it has an infinite number of significant figures. We can base our number on other things entirely. So the 3 sig figs in 2.54, the 1 significant figure in each of the metric conversions actually are immaterial because they actually have an infinite number of precision, an infinite number of significant figures. More often than not with unit conversion calculations such as these, our significant figure factor is going to be how many significant figures were in the original measurement. The original measurement here, 2 kilometers, had 1 significant figure, which means that our answer is going to have 1 significant figure as well. Which means that that 78,740 is going to round up to 80,000 inches. Why can't we go higher than that? Why can't we pare down to something a little bit more precise? Because our initial measurement wasn't very precise. We can't make a measurement more precise via calculation than it was initially when we measured it. Any questions with regard to this first practice problem? All right. Hearing none, let's move on to the second practice problem. What is the volume in cubic centimeters of a 14-pound block of gold? So in here, we've got two ideas. First of all, we have an idea of density. Now, we kind of skipped over density to get to this spot. We'll come back to it. Density is the mass of a substance divided by its volume. And so in broad terms, you're taking that base unit of mass and that derived unit of volume, dividing them by each other and getting a value that is very, very specific to a given substance. All substances have unique densities that are usually different from other substances. When we get to certain types of materials, we can see that densities get very, very close to each other, especially with organics. But for the most part, most substances have pretty unique densities that we can use to actually help us identify them. So what we can see here, though, is that in our formula for density, we have a natural fraction. And that natural fraction, mass over volume, leads itself to a good kind of conversion factor. Because anything that we can tie together in this kind of way, we can do two things with. First of all, we could turn this into an equivalence if we wanted to. We could say that for gold, (19.3 grams) is equal to 1 cubic centimeter. We could say that and be completely accurate in saying so. The other thing that this allows us to do, though, is using this equivalence, we can flip this fraction around based upon our need. So if I need grams in the numerator, I can write it this way. If I need grams in the denominator, I can write it in a slightly different way. I can flip the fraction. So that's what density allows us to do, is it allows us to take this concept of equivalence and apply it to do direct problem solving using dimensional analysis, using the equation to kind of guide us. So our first business here, we want to take our pounds and eventually turn them into cubic centimeters. To do that, we're going to take a side trip to figure out grams in between, because we do not have a relationship directly between pounds and cubic centimeters. But I can turn the pounds into grams, and then I can turn the grams into cubic centimeters using the density. So if I start with my 14 pounds of gold, my next step would be to use this conversion. 1 pound is 453.6 grams. Note that my pounds cancel. I'm left with grams. And in this case, notice I have grams in the numerator. So I'm going to want to use the version of the fraction that has grams in the denominator to get rid of the grams. 19.3 grams in 1 cubic centimeter. Again, multiply by everything in the numerator, divide by everything in the denominator. 14 multiplied by 453.6 divided by 19.3. My calculator jumbles out 329.036. My significant figure rules would tell me that I need to use the fewest sig figs possible. So I have 2 significant figures in my mass of gold. I have 4 significant figures in my conversion to grams. I have 3 significant figures in my density. Again, I'm limiting sig figs. So the measurement with the fewest sig figs is the 2. So I need to round to the second significant figure. 330 cubic centimeters is my answer. All right, any questions about this particular example? All right, hearing none here as well. Let's move on to the third example. Dan regularly runs a 5-minute mile, which means Dan is fast. How fast is Dan running in feet per second? Okay, so here we know the end goal. The end goal is that we want a measurement of speed in feet per second, feet divided by seconds. Now, a 5-minute mile is also some kind of conversion. What it says is that Dan is able to travel 1 mile in 5 minutes. So if we wanted to set up a fraction that was similar, where we had a distance in the numerator and a time in the denominator, we would use this kind of fraction to do just that. 1 mile in the numerator, 5 minutes in the denominator. Now we've got to do 2 things. We've got to convert our miles into feet, and we've got to convert our minutes into seconds. And luckily, these are 2 conversions that, yes, we are given some data on, but chances are we probably know them or know something similar to them already. So I'm actually going to go away from the plan here, so to speak, and use intellect and what I already know about some pretty common units to figure the rest of this out. So my first conversion, I want to get my minutes into seconds. And I know that there are 60 seconds in every minute. Now, be advised, Minutes is in the denominator this time, so I need the minutes to be in the numerator of my conversion factor so that it properly cancels. 1 minute is equal to 60 seconds. The other conversion of interest here, yes, I could go from miles to yards and yards to feet. I happen to already know, though, that there are 5,280 feet in every single mile. And most of you probably knew that at least at one point in time in your lives. Anyone who's gone through the American schooling system has learned about the common distances and the relationships between some of them. If that number didn't come to your head immediately, it's probably been a while since you used it. But it's definitely something that you probably knew at one point in time. So if you didn't get there, you could have used these two conversions as well. They would have ended up netting the same result. 1760 multiplied by 3 is 5,280. Before we do the calculation, let's make sure that everything cancels out that's supposed to. I've got minutes in the denominator here and in the numerator there, so they cancel out. I've got miles in the denominator here and in the numerator here, they cancel out. The only units that do not cancel are feet and seconds, which is exactly what I want, exactly where I want them to. Feet is in the numerator, seconds is in the denominator. Now we calculate. 1 times 1 times 5,280 divided by 5 divided by 60 to, unfortunately here, because of our measurements, calculator will spit out 17.6 here as your measurement. Unfortunately, with how this has been measured, 5 minutes with one significant figure, I'm going to have to round this. It would be 20 feet per second. All right, any questions about any of these 3 practice problems? All right, let's do another one of these then. Speed limit on Interstate 70 between Denver and Kansas City is 75 miles per hour for most of the distance. How many hours will it take to travel the 604.9 miles between the cities? And this is assuming that we are going to drive straight through. There's no changes in speed limit, no car accidents, no construction, pretty much nothing but, you know, corn, desert, and a couple of mountains there at the beginning. What we're ultimately doing here is we have a distance in miles that we want to convert into hours. Now, the key to that is going to be this speed, 75 miles per hour. Now, keep in mind, anytime you see that word per, you should automatically be thinking about division. Miles per hour indicates a rate of speed where I've got miles in the numerator and hours in the denominator. It's a division problem. Another way of thinking about this is that 1 hour's time is equivalent to 75 miles of travel distance. So to that end, just like we did with the density, we can use this relationship to ultimately help us to figure on just how much distance is being traveled and how quickly. We just need to use the fraction in the right way to get rid of the units that we are interested in getting rid of. So I have a distance of 604.9 miles. The only thing that can be used here is the speed to convert the miles into hours. Since I have miles in the numerator, I'm going to want to put miles in my denominator, put hours in my numerator here. 75 miles is equal to 1 hour. My miles cancel, my hours are remaining. 604.9 divided by 75 would give me 8.0653 and so on after that hours. From a significant figure standpoint, we have to weigh all of our options in terms of our conventions. How many significant figures do I have in this initial distance? Right. David says 4. Everybody else seems to be asleep. Right. Adria's got 4. Okay. Well, I'll take it from the two of you. Colby adds in as well. Yes. 4 significant figures in that initial measurement. How many significant figures in this measurement of speed? Right. Adria says 2. David says 2. Colby says 2. Trenton says 2. You're right. So we've got 2 significant figures in the speed measurement. We've got 4 significant figures in the distance measurement. How many significant figures do I need to round my time after the calculation to? Yes, Dale, you round to the fewest sig fig. So this would be 2, which means we're rounding to the second significant figure, which is that 0. So this is going to be 8.1 hours. All right. Any questions about this one? Okay. So here's what I want you to work on your own here. We've got a few minutes. I have a 1960 silver quarter. Has a mass of 6.25 grams. On any given day, the value of silver is worth $17.32 dollars per ounce of silver. If the coin is 92% silver, how much is the coin worth based upon its silver content? So one piece of information that you need that you do not have yet, we're gonna have to go back to our conversion table here. 1 ounce is equal to 28.35 grams. So we're gonna add that information here. And so take a couple minutes, try to solve the problem here. And when you get an answer, go ahead and throw it into the chat. And we'll see how everybody's doing in, say, about 5 minutes. So go ahead. All right. We do have the first correct answer thrown up in the chat, David. It is $3.52. Now, if you did the calculation to this point, and you did your gram conversion into ounces, your ounce conversion into dollars, what you would have ended up with is $3.82. However, this conversion assumes that all of the mass of the quarter is silver, which we are told here that it is not. Only 92% of it is silver. So we have to take this and multiply it by 92%. And if you take that and multiply it by 0.92 or 92%, you end up getting $3.51.2, which from a sig fig standpoint, we would round to $3.51. If you were at a jeweler or some kind of a silver collector, you might push them to try to round that penny up to 352. Either way, that's where you would end up going. Now, you technically could have applied this 92% at the beginning and said, okay, well, 6.25 grams was the mass of the quarter. If I take 92% of 6.25, I get 5.75. And done the conversion from there. But that's how you would have had to apply the 92%. Is somewhere along the line, you would have had to multiply that answer by 0.92 to account for the impurity of the coin from the standpoint of it not being pure silver. So that's we're going to call it a day for today. There are a couple of complex conversions like this that I would like to talk to, and we'll start with that on Friday. Keep in mind, Wednesday is going to be our first day of Chapter 2, and to that end, our first day of Chapter 2, we're going to be doing that virtually. I already have a YouTube video set up in our Chem 100 session, in our Chem 100 playlist that I want you to watch. And I'm going to put essentially a worksheet of some kind into Blackboard or Connect, probably Blackboard because it'll be easier to do, that I want you to complete as part of that. As far as Wednesday lab is concerned, those of you that are in my Wednesday lab, yes, I've arranged for a substitute. Dr. Tarbuck will actually be covering for me Wednesday afternoon. You will still be coming in the shift times that I mentioned before. So you'll either be coming at 2 o'clock or at 3:20, depending upon whether you're in the first shift or the second shift for that lab. Any other questions? All right, then. You are dismissed for the day. Keep up the good work. I will see you in person on Friday here in the classroom. Have a good day.